Okay, our fifth graph, called the rose. Kind of a misnomer. I think a better word for this would be a daisy, just because that's kind of what it resembles. All right, but a rose. If you have R equals, let's say A cosine of n theta. Let's say n is an integer. N is an integer, let's say, greater than or equal to 2. Start messing with negatives and such, I believe you still get a rose, but I want to talk about n being greater than or equal to 2. Because if n is 1, you don't have a rose. If n is 1, you have a circle that passes through the pole. I suppose you could call it a type of rose, but we're going to make sure that n value is greater than or equal to 2. Right? The other version is the sine version. A sine n theta. Right. Now, to spoil this, what roses look like, if this is the pole, they always pass through the pole. So you might get something like this. That could be a rose. Ugh. Not great. Or let's do a 4. You don't want to do it like that. Try a little bit harder. Let's try again. Let's go that route. There we go. That's not great, but you get the idea. Now, a rose doesn't have to have 3 or 4 petals. It can have, many, and I don't want to say any number of petals. We have to be careful how we say this, because there is a relationship between the number of petals you get and this n value. Right? So, for example, R equals 6 cosine of 4 theta. That is 4 times theta. Right? That is going to be a rose. And we can actually know how many petals we have by this number n right there, that n value. So, as long as we're dealing with integers greater than or equal to 2, no decimals or fractions, things get really weird very quickly. So, as long as we're dealing with an integer, 2 or greater, we can determine the number of petals that each rose is going to have. Obviously, we're talking about this being a petal, and that's kind of why I said maybe a better name would be a daisy, because that's kind of more what they look like than actual roses. But that's the idea. Well, as far as this n is concerned, we can say if n is even. 2, 4, 6, 8, 10, 12. Well, we got a 4. If n is even, then we say there are 2 times n petals. There's 2 times n petals. So if I were to graph this, and we could on our calculator, and we'll do something like this, I know that's going to have a total of 8 petals. 4 times 2 is 8, because n is even. Right? If n is odd, and we're throwing out the 1 again, right? We're starting at 2, so 3, 5, 7, 9. If n is odd, that should be a comma, then there are exactly the same number of petals. There are n petals. So there's certain numbers of petals you cannot obtain. Right? If I had, let's just put it on, R equals, you can even throw a negative in for the A, it doesn't matter. And we'll do a sine this time. Sine of 11 theta. Well, since 11, the n value is odd, this rose is going to have exactly 11 petals to it. So if it's even, you double it. If it's odd, it's the same number of petals. Now, there are a certain number of petals you cannot obtain. If I said, what would a 10-petal rose look like? Well, we can't say 10 theta, because if we do, 10 theta means it's going to have 20 petals. You can't say, well, let's call 5 theta. Well, now 5 is odd. It will have 5 petals. So a 10-petal rose, that's not attainable, not at least by the formulas we have here. Now, one other thing. This A value here also tells you something. It tells you the length of each petal from the pole to the outer edge, the absolute value of it. So not only if n is even or n is odd, let's put it underneath here. If the absolute value, I don't know why I'm saying if, the absolute value, make a definitive statement. The absolute value of A is the petal length. Petal length. It's going to be the length of each petal. So what I'm talking about is the distance from the pole to the outer edge. Whatever the absolute value of that A is, that will be the petal length. So if A is negative, like I said on this one, I know the petal is still going to be 3 units long. Right. So let's try a couple just to see what these look like. And this is where you're probably going to have to alter your window a little bit. Just because these things get a little bit more complicated. So let's try one here. I guess I could just go with, say 6 sine of 5 theta. I'll show you just here. So I'm going to graph 6 sine of 5 theta. Okay, what do I know about this thing? Well, number one, I know it's going to have 5 petals because n is odd. It's 5. If n is odd, it's the same number of petals. And I know each petal length is going to be 6 units long. So when I go to graph this thing, I'm not going to be real happy with the results. Right? Looks like a bird that's been squashed on the road. And that is definitely not what this thing should look like. Those sharp corners that you have there, I mean, it looks terrible. That is not what these polar graphs look like. And it doesn't even look like they're necessarily even passing through the pole. And the problem is your theta is too large. So if you take a look at my window here, I'm at a theta step of 15. That theta step is super important. You want a truer picture of this. You want nice, smooth petals, rounded petals. And they are rounded. It's a guarantee. They're not sharp corners here. These are all rounded. You have to change your theta step. Now, would 7.5 be good enough? I don't know. I'm going to go to 2. In other words, let's just go every 2 degrees and see if that doesn't smooth out my picture a little bit. Well, it definitely will, but by how much? Good enough? Still a little rough around the edges there, by the edge of the petals, but you can see, that improved it a little bit, right? And the smaller that theta step, the more truer the picture is going to be. And again, this is kind of a squashed version, squashed vertically because of the size of your viewing screen, right? It's wider than it is tall. So if you want a truer shape, do a zoom square. And you can see those petal lengths are 6. Actually, you can't see that. So let's go to the window, make the X max at 6. So I changed my X max to 6. I think I did. Did I change my X max to 6? Come on, stop. X min is -8. X max is 6. 8. Graph. Why are you not working for me? Now, you get the idea. The petal lengths will be the absolute value of that. So, sorry. That is not doing what I want it to do. 6. There we go. All right, we'll live with it. Okay, well, next shape. See if we can fit this one in. Number 6. This is called the lemniscate. Right, looks like lemniscate, but it's actually pronounced lemniscate. It's, I'm guessing German, just the pronunciation, lemniscate. What these look like, basically, you're going to get a figure 8. Figure 8, as it were. Like an infinity symbol. And they actually do, they can resemble this, but other times they can resemble something like this. Still an infinity symbol nonetheless for these lemniscates. They have a little bit involved type of formula. They actually start off with r squared equals, and then it goes, they put it in a squared, then a sine of 2 theta. Right. Because of this r squared, this is definitely not going to be a rose with 4 petals. Because of that r squared, this is totally different than what you're working with over here on the rose. Right. And the other one is r squared equals a squared cosine 2 theta. Right. So I don't know why I put the sine first and then the cosine second, but these are the figure eights. Now the sine will look like this diagonal figure eight. The cosine will resemble that sideways figure eight. Right? In the next video, we'll do some graphs of these and then wrap this up with the final graph, the last one, number 7.